Hello, my name is Julien Mouli-Castillo. I am a research fellow at the University of Glasgow in the James Watt School of Engineering. Today I will present to you some of my research interests and offer opportunities to work together on delivering the energy transition. So as a matter of personal introduction, I'm a French national living in the UK. I've been living in the UK for over 15 years now. My background is in environmental geosciences. I then went on to do a master's degree in carbon capture and storage at the University of Edinburgh, where I also completed a PhD, where we're looking at using geological formations to store vast amounts of energy using compressed air energy storage. I'm currently in a role where I'm seconded to the Lawrence Berkeley National Lab in California, and working jointly with researchers at Glasgow University and Edinburgh University. The key to a successful energy transition is to deliver clean, cheap, and secure energy to our societies. This is likely to be achieved by the rollout of renewables at scale, and in particular wind and solar, which are quite cheap. Unfortunately, the wind doesn't always blow when we need it, and the sun rarely shines in the evenings. So this mismatch between renewable energy supply and energy demand needs to be resolved in order to deliver a successful energy transition. This can be achieved in a number of ways. Via demand management, that is, asking users to adapt to the supply, such as using smart appliances that will turn on only at night, or reducing energy-intensive industries at times of short energy supply. And this has some impact on people's acceptance of green energy and on a country's industrial output. Another way is to use grid interconnections and upgrade. And this involves increasing the ability of our energy networks, whether gas or electricity, to move more energy from where it is produced to where it is needed more efficiently. In practice, this tends to involve a greater degree of connection with friendly neighboring countries, and these upgrades come at a cost. Another way is to increase the amount of dispatchable generation. So what is that? Well, it's simply energy sources that can be turned on or off on demand. For the most part, those are still fossil fuel plants, like gas-powered power plants, but they can also be renewables, like geothermal energy, which, unlike wind and solar, provides a steady stream of energy when we need it. The final option is to store renewable energy from wind and solar or purchase from neighbors when it is abundant and cheap, and to store it for later use. This storage solution takes place on a large variety of scales, from seconds to years, from a few watts for your phone to gigawatts that are enough to power an entire region. At the University of Glasgow, we're investigating technologies such as batteries, hydrogen storage, compressed air energy storage, and thermal energy storage. And my primary interest in today's talks is going to be to go over compressed air energy storage and underground hydrogen storage and see how they could potentially be integrated in a new way to deliver additional benefits and help this type of storage to be developed. So compressed air energy storage is a technology that, simply put, uses excess and cheap renewable electricity to power a compressor that compresses atmospheric air into, for example, an underground cavern. And when energy is needed again, it will expand that air into a gas turbine, for example, and generate electricity. So this is a technology that has the potential to serve as an electricity storage technology from the point of view of the grid. It can store energy for hours to days, which is quite a long time, and it can have a scale of hundreds of megawatts, which is enough to power many buildings or a small portion of a city. And it has the seasonal capability as well. So if you need to transition a lot of energy between summer and winter, it can use off-the-shelf components, but doesn't have to. And there is already 2 plants that have been operating for over 30 years in the world. And in the last 3 years, we've seen a doubling of the actual compressed air energy storage capacity, and all of this has been in China. So underground hydrogen storage is simply the storage of vast amounts of hydrogen in underground caverns. So this is an example of a salt mine. So this is what a salt cavity might look like underground. And this is the type of geological formation that we target when we want to store gases, for example, in the subsurface at scale that can be recovered rapidly. It's a form of chemical storage. Again, it can store energy for days to weeks this time. Also has seasonal capability, and there is some experience of storing hydrogen in these types of geological mediums in the chemical industry. So these underground storage technologies share the following common challenges. They have a high capital expenditure, which makes the risk of stranded assets in a rapidly shifting energy system with loads of innovative technologies more important than in a world that was dominated by oil and gas. Long lead times. So it takes time to plan, build, and commission these things in the order of 8 or more years. In many countries, large-scale energy storage has been subject to market uncertainty and regulations, making it difficult to develop competitive business plans and requiring the need for long-term contracts. Finally, the hydrogen supply chain is relatively mature in many areas, and this makes the development of storage projects as big as the ones we're talking about challenging due to the low amount of supply and the low amount of demand in this sector. Depending on the time it takes for the hydrogen economy to mature, it might become challenging and expensive to scale up the storage at the pace that is required, considering the long lead times that we've discussed above. So here is where we could collaborate together. We're currently developing a project and would love to hear from you if you are interested to contribute, whatever that contribution might look like. The project's working title is Multi-Use of Salt Caverns for Energy. It seeks to evaluate the technical feasibility and business plan for the synergistic development of salt caverns for compressed energy storage in the first instance, with a transition to underground hydrogen storage, but as part of the same project scope. The idea is to use a shared subsurface resource, which would allow for multi-use planning of the cavern. We will investigate the potential to lower environmental impacts through reduced cavern mining requirements and developing a system and a business plan that is more closely aligned with the evolving needs of the energy system and the hydrogen economy. Thank you very much for listening, and we look forward to hearing from you.